When Einstein first published the theory of relativity, he was either harshly mocked or ignored. Many believed the theory was too bizarre and unrealistic to be accepted. Some even claim that this guy isn't even a scientist, but merely a patent clerk, for daring to challenge the great scientist I.J. Newton. There have been theories proven correct for hundreds of years. So what is the theory of relativity? How was it formed? And what are its most significant consequences? Einstein, the great scientist who discovered the special and general theories of relativity, was born in 1879 in the city of Ulm, Germany. Shortly afterward, his family moved to Munich, where his father Hermann and his uncle Jakob ran a small but struggling electrical machinery workshop. To be accurate to say he performed poorly in school either. In 1894, when his father, but unable to endure the authoritarian education system at school, just a few months later, he moved with his family to live in Italy. Later, Einstein completed his studies and graduated from the Zurich Polytechnic in 1900. His argumentative nature and aversion to authority made it difficult for him to maintain good relationships with professors. As a result, despite being at the university, he was never offered a teaching assistant position, a traditional stepping stone toward a long-term academic career. 2 years passed, and he was finally hired at the Swiss Patent Office in Bern, though only in a rather minor position. In 1905, while working on this job, he wrote 3 important papers, which not only established him as a leading scientist but also sparked 2 revolutions in scientific understanding. 2 revolutions completely transformed our perception of space, time, and reality. At the end of the 19th century, scientists remained confident that they were on the verge of completing the overall picture of the universe. At that time, it was believed that space was filled with a continuous medium called the ether. Light signals and radio waves are both electromagnetic waves, just as sound is a pressure wave in the air. To fully complete the theory, the only thing left to do is to accurately measure the elastic properties of ET. The Jefferson Laboratory at Harvard University was constructed entirely without iron nails to avoid magnetic interference, serving experiments that require high precision in magnetic measurements. However, the builders did not anticipate that the reddish-brown bricks used to construct the laboratory, like most other buildings at Harvard, contained an extremely high iron content. The house is still in use to this day. However, it remains unclear exactly how much weight each floor of the library can bear without iron nails. By the end of that century, differing views about the ether, environment began to emerge. This theory posits that light travels through the ether at a constant speed. If you move in the same direction as the light in the ET reference frame, you will observe the speed of light to be slower than when moving opposite to it. However, a series of experiments designed to test this idea failed. Among them, the most precise and thorough was the experiment by Albert Michelson and Edward Morley. In 1887, at the Case School of Applied Science in Blavelin, Ohio, they conducted a comparison of the speed of light between 2 perpendicular beams. Because the Earth rotates on its axis and moves along its orbit around the Sun, the device will move in the ET system at varying speeds and directions. But Michelson and Morley found no difference in the speed of propagation between the 2 beams, whether measured by day or by year. Light appeared to always travel at the same velocity under all conditions. Based on the Michelson-Morley experiment, Irish physicist George Fitzgerald and Dutch physicist Hendrik Lorentz proposed the hypothesis that objects moving through the ether would contract in length and clocks would run slower. This contraction is similar to a clock running slower, which is precisely the reason we can measure the speed of light as always constant, regardless of how the light source moves relative to the ET reference frame. However, in his 1905 paper, Einstein demonstrated that if motion relative to the ether cannot be determined, then the concept of the ether becomes entirely meaningless. He proposed an alternative axiom, asserting that the laws of science must be the same for all freely moving observers. Specifically, they must measure the same speed of light, no matter how they are moving. The speed of light does not depend on the motion of the source and is always constant in all directions. This premise requires us to discard the notion that there exists a universal quantity called time which all clocks measure identically. Instead, each observer will experience their own distinct timeline. The passage of time for two individuals will be identical if they are at rest relative to each other, but will differ if they are in relative motion. Several experiments have confirmed this. One of these experiments proved that two extremely precise clocks, when moving in opposite directions around the Earth, would show different results. Upon returning, time had changed ever so slightly. This suggests that if you want to extend your lifespan a little, you should choose flights from west to east. At that point, the speed of the aircraft will be added to the Earth's rotational speed. LL have to endure the airline. Einstein's premise asserts that the laws of science must be the same for all freely moving observers. This is the foundation of relativity theory. Relative. This theory is highly regarded by many thinkers for its beauty and simplicity, but not everyone agrees, as opposing viewpoints still exist. Einstein shattered two absolute concepts of 19th century science, most notably absolute time, ET. And absolute time, also known as universal time, is the concept referring to the type of time that all clocks display identically. Does this mean everything is merely relative, with no absolute moral standards existing at all? This concern persisted throughout the 1920s and 1930s. Even when Einstein was awarded the Nobel Prize in 1921, the reason for the honor focused solely on one outstanding research achievement. But relatively minor in 1905. That commendation made no mention of the theory of relativity, which was still considered a highly controversial topic. However, the theory of relativity is now widely recognized by the scientific community. And its predictions have been validated through countless practical applications. One of the most profound consequences of the theory of relativity is the relationship between mass and energy. The scientist Einstein once asserted that the speed of light is always constant in all reference frames, meaning no object can exceed the speed of light. When we use energy to accelerate any object, whether it's a spacecraft or a tiny particle, the process unfolds as follows. The mass of the object will increase and hinder further acceleration. It is impossible to accelerate a particle to the speed of light, as this would require an infinite amount of energy. Mass and energy have an equivalent relationship, expressed through Einstein's famous equation, E equals mc squared. This is perhaps the only equation in physics that is widely recognized. One of the consequences is that if the nucleus of a uranium atom splits into two smaller nuclei, with a total mass slightly less than the original nucleus, an enormous amount of energy will be released. In 1939, as the threat of World War loomed closer, a group of scientists recognized the significance of its potential consequences. Convinced Einstein to abandon his pacifist stance and use his influence to sign the letter to President Roosevelt. This event led to the creation of the Manhattan Project, and as a result, 2 atomic bombs were dropped on Japan in 1945. Some people argue that Einstein bears responsibility for the atomic bomb, as he was the one who discovered the relationship between mass and energy. But how can we blame Newton for causing planes to crash just because he discovered the law of universal gravitation? Einstein himself was not involved in the Manhattan Project, and he was utterly horrified by the atomic bombings. After his groundbreaking series of papers in 1905, Einstein's name suddenly shone brightly in the scientific community. But it wasn't until 1909 that he received an invitation to take up a position at the University of Zurich, allowing him to leave the Swiss Patent Office. 2 years later, he moved to the German University in Prague, but in 1912, he returned to Switzerland, this time to teach at the Polytechnic University in Zurich. Although anti-Semitism appeared in many places across Europe, even within universities, he still maintained a strong reputation in academic circles. He received offers from Vienna and Utrecht, but ultimately chose to work at the Prussian Academy of Sciences in Berlin to avoid taking on teaching responsibilities. In April 1914, he moved to Berlin, and shortly afterward, his wife and 2 children joined him. However, after some time, their married life began to crack. Not long after, his wife and children returned to Switzerland to live. Although he occasionally visited home, Einstein and his wife eventually divorced. After that, he married his cousin Elsa in Berlin. In reality, during the war years, Einstein lived alone, free from family concerns. Perhaps this very fact allowed him to focus on his research and achieve many significant scientific accomplishments during that period. Although the theory of relativity perfectly aligns with the laws of electromagnetism, it conflicts with Newton's law of universal gravitation. The law of gravitation states that when the distribution of matter in a region of space changes, the alteration in the gravitational field propagates instantly throughout the entire universe. Instantaneity. In 1907, while still working at the patent office in Bern, Einstein recognized this difficulty. But it wasn't until 1911, while in Baja, that he truly began to seriously contemplate this issue. He noticed a close connection between ethnicity and the gravitational field. A person standing in a closed chamber, such as an elevator, would not be able to distinguish whether the elevator is at rest in Earth's gravitational field or being accelerated by a rocket in outer space. But you can't keep accelerating or letting the rope go slack in an elevator before disaster strikes. S-head due to gravity or because Newton and the Earth. However, the equivalence between acceleration and gravity no longer seems to hold true on a spherical Earth. Two people at points symmetric across the Earth's center will have opposite accelerations, but the distance between them remains constant. But upon returning to Zurich in 1912, Mr. Stang suddenly realized that the equivalence would hold true if the geometry of spacetime was curved, not flat as everyone had previously assumed. His idea was that mass and energy would bend spacetime in a way that needed to be clarified. Objects such as apples or planets always tend to move in straight lines through spacetime. However, their paths are bent by the influence of gravitational fields, because spacetime itself is curved. With the support of his friend Marcel Grossmann, Stang studied the theory of curved spacetime and the curved surfaces previously developed by George Friedrich Grimond. However, Grimond focused solely on studying public space, whereas Stang discovered that both space and time possess a public nature. In 1913, Stang and Grossmann published a paper proposing the view that the gravity we know is essentially just a manifestation of one truth: spacetime is curved. However, due to Mr. Stang's error, they were unable to derive the equations relating the curvature of spacetime to the mass and energy within it. Mr. Stang continued his research on this issue in Berlin, where he was free from family distractions and less affected by the war. Finally, he precisely discovered these equations in 1915. He discussed this idea with mathematician David Hilbert during his visit to the University of Göttingen in the summer of 1915. Notably, Hilbert had independently derived similar equations just a few days before Stang. However, as Hilbert himself acknowledged, the true credit for developing the new theory belongs to Stang, the one who proposed the idea of linking gravity to spacetime. This is also a significant contribution to Germany during a time when such scientific exchanges and discussions were still maintained, even in wartime. This is completely contrary to the national chaos of the 2 decades that followed. The new theory of spacetime is called general relativity to distinguish it from special relativity, the original theory that did not include gravity. In 1919, a British expedition traveled to West Africa and observed the phenomenon of light from a star bending as it passed near the sun during a solar eclipse. This officially and clearly confirmed Einstein's theory of relativity. This is undeniable proof that spacetime is curved. And that marked the greatest turning point in our understanding of this universe since Glid wrote his foundational work on geometry around 300 BC. Einstein's general theory of relativity transformed space and time from a passive backdrop, where events simply occur, into active elements that contribute to the workings of the universe. This poses one of the greatest challenges in 21st century physics. The universe is filled with matter, and it is this very matter that bends spacetime, causing objects to attract and fall toward one another. Mr. Stein realized that his equations could not find any numerical solution to describe a static, unchanging universe. Rather than abandoning a static universe, a notion he and most others had believed in, he adjusted the equations by introducing a cosmological constant. This constant exerted a repulsive effect on spacetime, causing objects to tend to push apart. This repulsive effect of the cosmological constant can balance the attractive force of matter, thereby producing a static solution describing the universe. This is a major mistake in theoretical physics. If Mr. Stein had stuck to his original equations, he might have predicted that the universe is either expanding or contracting. It can be affirmed that the hypothesis of a universe evolving over time was only seriously studied after scientists conducted observations using the 100-inch telescope at Mount Wilson in the 1920s. These observations show that the farther away galaxies are from us, the faster they move away. This indicates that the universe is expanding, causing the distance between galaxies to increase over time. This discovery eliminated the need to use the cosmological constant to obtain a static solution for the universe. Later, Stein admitted that introducing the cosmological constant was the biggest mistake of his life. However, it turns out this might not be a mistake after all. Recent observations suggest the possible existence of a small cosmological constant. The theory of general relativity has completely transformed how we discuss the origin and future of the universe. A static universe could have existed eternally or been formed in the past with a form indistinguishable from the present. However, if galaxies are moving away from each other as they are now, it suggests that in the past, they must have been closer together. About 15 billion years ago, they must have been compressed together with an extremely high density. Primeval atom. He was a pioneer in researching the origins of the universe, also known as the Big Bang Theory. Mr. Stang doesn't seem to have ever given the Big Bang Theory much serious thought. It seems he believed that if one were to trace the motion of galaxies backward in time, the simple model of a uniformly expanding universe would no longer hold true. Even a small sideways velocity of galaxies is enough to make them drift apart. He suggested that the universe had undergone a contracting phase in the past before transitioning to its current expanding state, at a certain moderate density. However, today we understand that it was the nuclear reactions in the early stages of the universe that produced the abundance of light elements we observe today. The density must reach at least tens of tons per cubic meter, while the temperature must rise to tens of billions of degrees. Moreover, observations of the cosmic microwave background suggest that the density of matter could once have reached billions of tons per cubic meter. According to Einstein's general theory of relativity, the universe cannot transition from a contracting state to the current expanding phase. Roger Penrose and Stephen Hawking proved that general relativity itself predicts the universe originated from the Big Bang. Thus, Einstein's theory essentially implies that time has a beginning, though he himself was not satisfied with this idea. Einstein even asserted with certainty that the general theory of relativity includes predictions about time. The lives of massive stars end when they can no longer radiate enough heat to counterbalance their internal gravity, causing them to collapse. Einstein concluded that such stars would inevitably reach an end state. However, we now know that stars with more than twice the Sun's mass have no final state of existence. They will continue to shrink until they turn into a black hole. The space-time fabric becomes so warped that not even light can escape. Penrose and Hawking proved that, according to general relativity, time would cease to exist upon entering a black hole. This holds true for both the star and the unlucky astronaut who falls into it. However, the equations in general relativity do not allow us to determine when the universe was formed or when it will end. Therefore, that theory also cannot predict what consequences will occur after the Big Bang's absolute freedom in determining the universe. However, some argue that the origin of the universe must necessarily follow laws that remain immutable throughout all ages. We have made some progress in this direction, but we still do not fully understand the origins of the universe. General relativity cannot explain the Big Bang because it is incompatible with quantum mechanics. A major turning point in awareness occurred in the early 20th century. Quantum theory began to take shape in 1900 when Max Planck discovered that radiation from a hot glowing object could only be accurately explained if light was assumed to be emitted or absorbed in discrete packets, called quanta. In a groundbreaking paper written in 1905, while he was working at the patent office, Mr. Stang demonstrated that Planck's quantum hypothesis could potentially explain the photoelectric effect, where light shining on certain metals causes electrons to be ejected from the surface. This is the foundation of modern projectors and today's film cameras. Thanks to this research, Mr. Stang was honored with the Nobel Prize in Physics. Mr. Stang continued to research quantum ideas into the 1920s, but Werner Heisenberg's work in Copenhagen deeply unsettled him. Paul Dirac at Cambridge and Erwin Schrödinger in Zurich were the ones who built a new vision of reality called quantum mechanics. The tiny particles no longer have a definite position and velocity. Instead, the more precisely we determine their position. At that point, the more inaccurately their speed was determined, the more the opposite held true as well. Mr. Stang was utterly astonished by these random and indeterminate factors in the fundamental laws. God does not play dice. However, the majority of the scientific community has acknowledged the accuracy of these newly discovered quantum laws. Because they not only explain a series of previously inexplicable phenomena but also perfectly align with actual observations. These laws are the foundation for the development of modern chemistry, molecular biology, and electronics, while also serving as the basis for technologies that have transformed the world over the past half-century. In December 1932, realizing that the Nazi Party and Hitler were about to seize power, Ernst Stang left Germany. And 4 months later, he renounced his German citizenship to spend the final 20 years of his life at the Institute for Advanced Study in Princeton, New Jersey, USA. In Germany, the fascist regime launched a campaign to eradicate science founded by Jews, while also targeting many German scientists of Jewish descent. This is one of the reasons Germany couldn't develop the atomic bomb. Stang and the theory of relativity were the targets of this campaign. 100 arguments against Einstein. Why does it have to be 100? If I'm wrong, even one mistake is enough. After World War II, he proposed that Allied nations establish an international organization to control atomic weapons. In 1948, he was invited to serve as the president of the newly established State of Israel, but he declined. Politics is only temporary, but mathematical equations are eternal. The world has undergone profound changes over the past 100 years, far surpassing any transformations of previous centuries. That does not stem from new theories of politics or economics, but rather from remarkable technological advancements driven by breakthroughs in fundamental science. No one could better embody those monumental advancements than Albert Einstein.